All right, so in this one, we're going to look at a big theorem that ties a bunch of different ideas together. So we'll take 2 clips to do it. And we need a couple of new terms. So the first one is simply connected. And we say that a set is simply connected if it has no holes, but there's a little bit there that you have to be careful with. So what I'm going to say is that we're going to require the set to be connected. So this means that whatever my set is, if there's 2 different points, then there has to be some kind of parameterized path that goes from one to the other without ever leaving the set. So that's my meaning of connected. And then open, this means as opposed to closed, in the sense that this contains no points of its boundary. So we want the set to not contain any points of its boundary. So in other words, this is something that we would usually draw with like a dotted line to indicate that none of those boundary points are included in there. And then if that's the case, then that means for any point in the set, I can find a little ball around it that's centered at the point and completely contained inside the set, right? Like if I were allowed to choose a boundary point, then I couldn't do that because I might have a situation where no matter how small I make the ball, there's some junk out here that's like poking outside the set. That would be bad. That's why we don't want the boundary points. Basically, given a point in the set, we want to be able to do a little epsilon wiggle in either way so that we can take a limit without going outside of the set. Okay, so if we have a set D, which is both open and connected, then we say that it's simply connected if it has no holes. And that's exactly the kind of thing that you understand when I say that it has no holes. Just the basic intuitive thing. So if I have a set like this, then this set is open and it's connected, but it's not simply connected. It fails to be simply connected because it has this hole in the middle that's punched out. And so, speaking of punched out, if I take a set that's connected and then I remove like a single point, boing, and maybe that one's cut out. So suppose this is like R2 except minus the origin, then that would be an example again of something that's not simply connected. Maybe I should say not. These are examples of failing to be simply connected. And we're going to be interested in the situation where the vector field is defined on a simply connected set. So in other words, that means if there's holes punctured out of its domain, then that'll be the problem. Okay, so that is simply connected. The other idea we need is for a vector field to be exact. So a vector field is exact if and only if its components, P and Q, satisfy this relationship right here, that dq dx is equal to dp dy. And we'll see why this comes up in just a moment. All right, so now the statement of the theorem begins as follows. The setup is, suppose we're looking at a situation where we've got an open and connected set, and we've got a vector field with some components we're going to call P and Q for sake of argument. Okay, then the following are equivalent. Okay, so that means that any of these conditions implies any of the others. So number 1, F is conservative. And so we know that this means, that there exists some little f such that f looks like capital F looks like its gradient. Okay. 2, that that the integral of f dc is path independent for any c. Okay. 3, that the closed loop integral is always 0. And that has to be true for any curve C. And then the last one is not necessarily equivalence. Let me say if f is conservative, then f is exact. So that's, in other words, we're saying that the forward direction holds. So f being conservative implies f is exact. But we only get the reverse if we also assume simply connectedness. So if D is also not just open and connected, but has no holes. So if D is simply connected, then whenever f is exact, it follows that f is conservative. Okay. So when I say that the following are equivalent, it means that any one of these implies any of the others. So if you show me a vector field and it happens to be the case that its integral vanishes around any closed loop, then I know, oh, then that means there has to exist some little f such that it's the gradient of that little f. Or vice versa. If you tell me I'm going to be looking at this gradient field, then I know, oh, if I look at the integral of that thing around any closed loop, it's going to be 0, just like we were talking about with work in the other clip. And then if we know that our set has no holes, then the idea of being conservative is the same as the idea of being exact. So in other words, if there's no holes and I check this little equation, then that means that I know that f is the gradient of something. And we'll see that if f is the gradient of something, then it's always the case that the component test holds. And that, we will see, follows just from the equality of mixed partials.